Hi, welcome to this class. In the last class, if you remember, we have seen lithography, right? And I told you that we will look at the micro machining, there is bulk micro machining and surface micro machining, in particular etching. So, when you etch the material, either you etch the bulk of the material or you etch the material which is deposited on the substrate. So, surface of the material to pattern, then it is surface or bulk micro machining, but anyway when you have to pattern it, you have to etch it. So, that is called etching. Now, we have two types of etching, one is wet etching and one is dry etching. In wet etching, suppose we are going to etch silicon, right. So, silicon you have potassium hydroxide, tetramethyl ammonium hydroxide, which is called TMAH. KOH is used at 80 degrees centigrade and TMH is done at or used at 25 degrees centigrade at room temperature, but the TMH is a neuropotent. So, we need to be careful about chemicals when we use within the hood, and in particular when there is a wet bench, there is a way to operate or use the chemical within the bench. Okay. Sometimes I see that people use their head within the hood which is not really okay, because the way to operate is just put your hand inside and not your head inside, so that the gases or the VOCs that comes out right from that particular chemical is goes out through the filter, through the exhaust, and you are not breathing it, right. Just a hand should be inside, not your face. So, anyways, before we go and understand these separate things, because some of the devices that we are going to talk about in this course does not really require you to do a etching process. So, we will keep that etching a little bit, we will discuss this etching process a little bit later, but right now let me show you to you a process step to design a simple interdigitated electrodes. Okay. Now, why to look into that? So that when we see this process flow, you will again recall what we taught, what we have learned in the lithography lecture, and how we can use that learning to design or pattern a material that is deposited onto a substrate. Okay. So, with that focus in mind, let us take an example of an interdigitated electrode. Now, let me show it to you what exactly interdigitated electrode means. So, you see these are digits, right. So, 1, 2, 3, 4, 5, these are digits. This is interdigit, okay, interdigit. So, now if you have many fingers like this, right, becomes interdigitated electrodes. Okay. Now, why we say it is electrode? Because if this is the lines are metal, right, and if it is not touching, the resistance is infinite. When it is touching, it is short circuit. When you place any material on this interdigitated electrode, you will see the change in the resistance depending on the resistance of the material, is not it. So, now the question is how to design this interdigitated electrodes, or let us take an example of aluminum, and then I will show it to you. If you again recall the CVD, we have just understood what kind of CVDs are there, and in particular PCVD, which is used at room temperature, right, or not really room temperature, 100 degree centigrade, lower temperature, 100, 200, 300 degree centigrade compared to the other CVDs. Where we can use PECVD and why PECVD becomes very important for certain processes. Okay. So, we will see example of aluminum, and on aluminum we will deposit a silicon dioxide, okay, and then see that how we can utilize the understanding of the previous classes for designing this particular electrode. So, if you see the screen, we will talk about interdigitated electrodes. Okay. So, if I just show you the top view, it should look like right. and we should have some contact pads. We should have contact pads. So, let us have contact pads. So, this is the structure we want to pattern. Now, when I draw the line, this line, if you zoom in, it has a width and spacing, right. So, suppose let us say I just take this section and I zoom in, how it looks like? It looks like this. Okay, this looks like this. Now, what we need to understand is what is the width of this, right, and what is the spacing. So, let us say width is 10 microns, spacing is 5 microns, right. So, this now if you are looking at the biosensor, the closer the electrodes are, the better the sensitivity for certain applications, but let us not go into that right now. Just understand that when you have interdigital electrodes, the width and the spacing between electrodes is important. Now, if you want to do this, let us start the process. Okay. So, we start, and this is the oxidized silicon wafer. Assume that the substrate is your oxidized silicon wafer. Okay. And this interdigitated electrode is made up of aluminum interdigital electrodes, right. So, let us start. So, first step is you take a silicon wafer, we will draw the cross section. Okay. This is a top view. So, you have your silicon as a substrate, then you of course do pre-cleaning and you dip this wafer into HF, right. I told you HF. What is HF? HF is hydrofluoric acid. When you dip the wafer in HF for certain seconds, the native oxide, the oxide that is grown onto the silicon because of the presence of oxygen in the atmosphere, right, that oxide, which is native oxide, can be etched because hydrofluoric acid is the etchant for oxide. So, when you dip the wafer, the oxide will get etched. Now, you take the wafer out, dip it in the DI water or rinse it with DI water, dry it with nitrogen, and then do the pre-bake, so that the moisture is gone, and then you start your process. So, next process is we will perform thermal oxidation. Thermal oxidation is a technique by which we grow the silicon dioxide on silicon, all right. So, it is a furnace, and in furnace you can load many wafers, close to 25 wafers, and then initially the temperature is raised to 900 to 1200 degrees centigrade, in that range. When the temperature is raised, nitrogen is flow in the tube, because a horizontal tube furnace, and when the temperature is reached, then the nitrogen is stopped and oxygen flows through the tube. When oxygen reacts with silicon, it becomes silicon dioxide. This is a dry oxidation process. So, Si plus O2 gives SiO2. But if you want to, so that is the advantage, the quality of the silicon dioxide is better. When we go for wet oxidation, then is water vapor which is carried into the horizontal tube furnace. So, Si plus H2O gives SiO2 plus H2, but we have to balance the equation. So, you have to write down Si plus C, H2O gives SiO2 plus H2. Si plus H2O shows you SiO2 plus H2. Now, we have to balance it. So, we say 2H2O, right. So, here is 2H2, right. So, 4O2 SiO2, easy. This goes as a exhaust. So, this is a wet oxidation, wet oxidation. In case of dry oxidation, Si plus O2 gives SiO2. This SiO2 is the gas, right. This is the water vapor 2H2O. Okay. So, this is how the silicon dioxide is formed, but this process, dry process, the quality is really good. Okay. Here the thickness can be close to 2 microns, 1 to 2 micron. Here thickness is comparatively less. Okay. So, again we will use this process is called thermal oxidation. Thermal oxidation. Okay. So, we will look into thermal oxidation process, that is erase this because we require this space for our process flow. So, the next step 1 is to take the silicon wafer, then clean it or pre-clean it, then remove the native oxide, then pre-bake it, followed by thermal oxidation. So, step 1. Step 2 is we have grown thermal oxide. Now, when you take the wafer and you place the wafer into the chamber or into the furnace, horizontal tube furnace, the oxide will grow on both the sides. Why? Because oxygen will react with silicon on front and back side of the silicon. So, you can grow silicon dioxide front and back. Now, we will take an example of wet thermal oxidation, so that we have about 1 micron thick silicon dioxide. Okay. Next step is we will deposit aluminum. Now, if you want to deposit aluminum, what is a way to deposit aluminum? Can you recall from our previous lectures, right? You can use physical vapor deposition. Okay. This is SiO2 over silicon, physical vapor deposition. So, SiO2 over silicon is oxidized silicon wafer. Okay. So, do not get confused. PVD, we can use in PVD thermal oxidation, is it oxidation? No, thermal evaporation. With thermal evaporation, you can deposit aluminum onto the oxidized silicon substrate. This is aluminum, SiO2, silicon, SiO2. Okay. Using what? Thermal evaporation. Okay. Nice. This is our step number 3. Next step we go next slide. Alright. Next slide is we will draw again oxide layer. Once you understand this process, it becomes very easy to fabricate lot of devices and pattern lot of materials. Okay. So, that is why I am drawing each step again, and I am taking enough time so that I hope you understand. This aluminum layer on aluminum. Now, you have to pattern the aluminum, right. So, if you go back and if I draw the this one, the cross section of this one, how it will look like. Okay. This will look like this. This one is your aluminum InterDigitated electrodes, silicon, and that this layers are SiO2. Okay. So, we want this particular pattern starting with the silicon. So, silicon oxide, aluminum deposition. On aluminum deposition, or aluminum which is deposited as a thin film, we will spin coat photoresist. Positive photoresist, we will spin coat positive photoresist. This is our fourth step. After spin coating photoresist, what is the next step? You remember, soft bake. Soft bake, right. Next step, what was the next step after soft bake? Mask, no. So, we require a bright field mask. Why I am saying bright field? I will show it to you. This is our oxide. You do not need to write down every time like this. If you correctly give different patterns, for example, on the side you will say, okay, this is my silicon, then this is my silicon dioxide, then this is aluminum, then this is photoresist. Then we do not have to mention every time, okay, if you when you draw the process flow. Okay. So, SiO2, on that we have our aluminum. What happened here? Aluminum. On aluminum we have photoresist, which is already soft baked. On photoresist we will load the mask, okay, and I said what? Bright field mask. So, field is bright, pattern is opaque or dark. Field is bright, pattern is dark. Okay, bright field mask. Now, once you load the mask and align the wafer, next step is expose it. Expose using what? Expose using UV light, ultraviolet light. Once you expose the photoresist, which is a photoresist here, photoresist, and that is also positive photoresist, right, with UV light, the unexposed region will become stronger, right, the unexposed region will become stronger. So, after exposing with UV light, you unload the mask, and next step is, we write down here or draw here, you dip the wafer in a photoresist developer, correct. We dip the wafer in photoresist developer. When you dip the wafer in photoresist developer, what will happen? The photoresist will get patterned similar to your mask, correct, because unexposed region becomes stronger. The next step is hard bake. Hard bake 120, 1 minute, hot plate, and after hard bake you dip the wafer in aluminum etchant. After hard bake, you dip the wafer in aluminum etchant. When you dip the wafer in aluminum etchant, what will happen? Okay. The area which was not protected by photoresist, you see this area which is not protected by photoresist, the area which is not protected by photoresist will get etched in the aluminum etchant, means the aluminum which is not protected area. When what is area is aluminum, right, the aluminum is deposited in this particular on this particular oxidized silicon substrate. So, the aluminum which is not protected by the photoresist will get etched, and aluminum which is protected by the photoresist will not get etched. So, after this the next step is, so the role of photoresist is to act as a mask, to act as a mask. Okay. Now, the next step, so we are at 6th and 7. Step 7, right, 6 and 7, and next step is that we need to strip the photoresist. So, if you want to strip the photoresist, we will dip that wafer in acetone. Which one? We will dip this one as a next step in acetone. Okay. If we dip the wafer in acetone, what we will have? Acetone is the stripper for photoresist. Okay. Acetone is stripper for photoresist. So, what we will have is okay, aluminum interdigitated electrodes. You see, now let us say this is 8. Now, you see this and remember, okay, this pattern you remember. Let us go back, one step back, two step back. See, this one is similar to our 8, isn't it? We have oxidized silicon substrate on which there is a aluminum interdigitated electrodes. So, that is what we have got here also. So, this is the beauty of lithography, that you can pattern the aluminum material or any other material per se and get the different structures. Now, let us take an example of this PCVD and its advantage. Okay. I want to now deposit a silicon dioxide, a grow silicon dioxide on this particular wafer. So, if I go for any other CVD techniques, right, then you know that the temperature is greater than 700 degree centigrade. But if I heat the wafer so that I can have, so what I want is, I will show it here, this is what I want. Okay. I want my aluminum interdigitated electrodes to be covered by silicon dioxide. To join 2 points. Okay, good. Now, this is our silicon dioxide. Okay, the dotted region is a silicon dioxide. So, this is silicon dioxide that I want on this particular aluminum interdigitated electrodes. But as you know, silicon dioxide, this thermal oxidation, this one, this silicon dioxide is using thermal oxidation, and thermal oxidation the temperature is 900 to 1200 degrees centigrade. If I heat this particular wafer, which is wafer number 8, here is the step number 8, wafer which has reached step number 8. If I heat this wafer at 1200 degrees centigrade, 900 degree, even at 700 degrees centigrade and above, what will happen? The aluminum interdigital electrodes will melt, because aluminum melting point is comparatively lower. So, in this case I cannot use my thermal oxidation technique. So, what are the alternatives? Right? One alternative is you can go for sputtering, and second alternative is you can use PECVD, plasma enhanced chemical vapor deposition. We can use plasma enhanced chemical vapor deposition, because PECVD can be used at 100 degree centigrade to 200 degree centigrade, and this temperature will not affect the aluminum interdigitated electrodes. So, if I go for PECVD or if I go for sputtering, because in sputtering also you can deposit silicon dioxide, right, either with plasma enhanced chemical vapor deposition or sputtering is a physical vapor deposition. If you want to have a better step coverage, then PECVD is better, as you know, correct. So, if I go for PECVD and if I perform the chemical reactions into a chamber which is at 100 to 200 degree centigrade, then what will I have? I have my aluminum interdigital electrodes covered with PECVD oxide, covered with PECVD oxide. Correct. Now, let us understand that suppose there is oxide everywhere, but I cannot take the contact out now, because the oxide is also on the contact pad. So, I have to remove the oxide from the contact pads, is it correct? Because oxide is everywhere, I have to remove the oxide from both the contact pads. So, to do that, what is the process? So, let us understand the process. So, in that case I will have oxidized silicon substrate with aluminum interdigitated electrodes, and I only want the contact pads to be free of this silicon dioxide, or silicon dioxide should only be etched from the contact pads. This is my SiO2, which is PECVD oxide. This SiO2 is thermal oxidation, silicon, and this one is my aluminum interdigitated electrode. So, what I will do is I will spin coat photoresist. Okay. Again I will spin coat only positive, you can use positive or negative, but I will spin coat for positive photoresist. After that I load the mask, is not it? I have to load the mask, and if I have positive photoresist, then I load the mask in this fashion. That means I will design my mask in this fashion. I will use a dark field mask, okay. And I will tell you what is the reason of using the dark field mask. Okay. This is my dark field mask. Now, I will expose this with UV light. Okay. Expose the photoresist which is below the mask, right, with a UV light. Now, when I say that we will spin coat the photoresist and load the mask, it is assumed that we will perform the soft bake, which is a 90 degree centigrade, right, 1 minute on hot plate. Then when we expose it, what will happen? The unexposed region will become stronger and the exposed region will become weaker. Why? Because we are using the positive photoresist. So, when I dip this wafer in photoresist developer, what will I have? I will have oxidized silicon wafer with an interdigitated electrodes and now you see, okay, what will happen. Our oxide is there, right, and the area which is not exposed of the photoresist will become stronger. So, I will have here, I will have here and I have here. What is this? This is the area of the photoresist which was not exposed. Since it was a positive photoresist, we will have the similar pattern like our mask, right. So, positive photoresist stays in the area which was not exposed. The area which was exposed to light, right, that particular photoresist becomes weaker and it gets developed in the photoresist developer. After this step, you know what to do, you have to perform the hard bake. After hard bake, if I deposit or if I dip this wafer, not deposit, if I dip this wafer in buffer hydrofluoric acid, BHF. BHF is the silicon dioxide etchant. If I dip this wafer in BHF, what will happen? I will have my silicon dioxide, interdigitated electrodes, oxide layer, and the photoresist, okay, correct, because here the oxide is not protected by the photoresist. So, when you dip the wafer in BHF, the oxide will get etched. Once you do that, the next step is you dip this wafer in acetone. So, when you dip this wafer in acetone, what you will get? And if you have noticed something, what you have to notice? That the oxide layer which was the bottom, this one also got etched, you see, because that oxide layer was not protected. So, it will get etched in the buffer hydrofluoric acid. What will I have? I will have my contact pads open, right, and other area is not open. I am just giving you example. Okay, I just wanted to have the contact pads. I do understand that this whole design, right, will be of not further use, because we have covered the interdigital electrodes with the silicon dioxide, right. I just wanted to show you the example of how to use the dark field mask and how to take the contact pads out, right. These are contact pad 1 and contact pad 2, correct, from the interdigital electrodes. But how to use the bright field mask and how to use the dark field mask, that was the whole purpose of showing you this particular pattern. All right. Now, I hope that you understood how to deposit a metal, how to use the lithography system or process, and with that how to pattern it. If I want to go for silicon dioxide on metal which is having a lower melting point, then PECVD or sputtering is better. And if I want to open the contact pad, how to design the mask and how to expose it and what are the process. So, with this I will stop it here. In the next class we will see example of micro electrode arrays, high density micro electrode arrays that can be used for acquiring the neural signals. So, till then I take your leave. I will see you in the next class. Bye. Done.